and our second talk is going to be on Fantômas, probably mispronouncing that, understanding face anonymization reversibility.
Yeah, thanks for the introduction. Can you hear me? Okay. Well, yeah, I'm Julian, and I'm going to present our investigation into reversibility of face anonymizations. So let's say we are a user and we share our biometric data online to gain some kind of utility. For example, we are playing a VR multiplayer game, or we're sharing images of ourselves on social media. And because we care about our privacy, we anonymize that data. So for example, we apply some anonymization method, which even claims differential privacy on the internet. So that method removes half of our pixels randomly, and we think that's safe, right? And well, maybe there's an adversary and they also look at that image and they think, well, actually, if I interpolate all the completely black pixels, then I get something like this again, and on that I can run just face recognition, and obviously I can identify the user. And that actually works even with other anonymizations, for example, blurring or noise, where we can get significantly close to the original image. And this obviously completely breaks the anonymization. Anonymization has to be a one-way function which removes all the identifying information. And so if we can reverse the anonymization, this is kind of worst case failure for it. So this is what we wanted to investigate. We first want to know, well, which anonymizations are reversible and what are reasons why this is happening so that we can avoid it in the future. So what I've shown before as reversing was kind of de-anonymizations which were specific to the anonymization. So we have some de-blurring methods, denoising, or super resolution, which are approaches which we take from the computer vision community. But if we want to investigate kind of generally which anonymizations are reversible, well, we don't have anything for that. So we need a general de-anonymization, and what we do is we use a machine learning model, which is the same architecture which we can train then for any anonymization method. And what we use is a simple convolutional autoencoder with an additional linear layer in the middle, which is purposely a simple design so that we can better understand what is actually going on. So our adversary model is that users share their data publicly, anonymized data, and then our attacker wants to identify the users. And our attacker has some additional access to data. They have other images of the individuals they want to identify, so that they have something to compare to. And they also have an additional background data set with images of other people. And they also have an anonymization oracle, which we can use to anonymize images, just like you might have an encryption oracle in cryptography. And so what the attacker can do with that information is they can create an anonymized background data set, and then they have pairs of anonymized and clear data, which they can use to train that machine learning model which I showed on the last slide. And then when they have that trained model, they can use that on test data to de-anonymize the images before running the recognition method on them. So what does our experiment setup look like when we investigated this? Well, we had the original data, we anonymized it, then we split our data up into two sets, one of which we used to train the de-anonymization, the other one we de-anonymize and then recognize the images on. We test all of this with two different data sets, so we have some comparison, and in total we test 15 different anonymization methods, which were chosen to be representative of different groups of face anonymizations which we found in the literature. In addition to the general model which I showed you, we also tested some other de-anonymizations, some which were specific to specific methods, but this is something for you if you want to read the paper. We also tested different recognition models so that we don't rely on one and we report the average of them. We define a reversibility metric, which is defined by first measuring recognition accuracy on clear data and anonymized data, and then de-anonymized will be somewhere in the middle, and then essentially reversibility is how close can we get back to clear level starting from anonymized level. So something that the anonymization which we can reverse perfectly would be 100% reversible. Alright, let's look at some results, and we start off with some basics, which are permutations, which are very clearly fully reversible, but which shows that our method actually works, and we can achieve very high reversibilities. But also interesting are, of course, some of the basic methods which you can see every day, like blurring, eye masking, pixelation, and noise, where we find also very significant reversibility scores, some of them actually very high, for example for noise, where you can show, well, if you use essentially with the parameters shown here, use them, then we can just reverse them and still identify you, which is something to keep in mind. We also investigate some methods based on differential privacy, where we also find reversibility scores significantly higher than what the guarantee might claim to achieve. But we also find anonymization which are actually irreversible. For example, methods based on k-anonymity, where we kind of layer different faces on top of each other, have very low reversibility scores, and also methods which remove the entire face and replace it by newly generated synthetic ones are irreversible. And now we were interested in, well, why are these methods potentially reversible? And well, if we look at the permutations, well, we see we don't actually remove any of the identifying information, we only obfuscate it. And the obfuscation obviously means that the originally trained machine learning model will not be able to recognize individuals anymore, but the information is still there, and if we put it back in the right place, the identification works again. For the other basic models, we find, well, we do use some identifying information, but there's still enough identifying information left that we can reconstruct some of the removed information. For example, if you move one eye, well, I can reconstruct the other eye because I know what kind of eye color you have and what it generally looks like. For the DP methods, we see, well, obviously this seems to be a formal guarantee that's in this case not really suitable. If you define your neighborhood based on the pixels which are next to each other. We also considered if there is a trade-off between reversibility and utility. So for utility, we, based on previous work, we did a user study where we showed participants anonymized images, and we asked them whether the image showed a naturally human being, and then we can plot this in a reversibility utility graph with utility on the x-axis and reversibility on the y-axis, and if there was a trade-off, we might expect to find some kind of trend in this plot, but in fact we find both anonymization methods like the synthetic generation ones, which have which are irreversible and have high utility, but also anonymization methods which have high utility and have high reversibility. So, as I come to the end, some takeaways. The evaluation of reversibility was previously missing when we evaluated anonymizations, but this is very crucial because we find that 11 out of the 15 tested anonymizations were reversible. Some reasons for that were that information was only obfuscated, or that not all information was removed, and we also find some reliance on unsuitable formal guarantees. And for what we tested, there was no trade-off between reversibility and utility. If you want to read more, there's obviously a paper that you can read. If you have anonymization and you want to test whether it's reversible, we have a software framework that you can use for that. And now I'm happy to answer any questions that you might have. Thank you.
Hi, thanks for the great work, and it's very interesting. I actually had like a very similar attack from what it seems on trajectories a few years ago. And what we found back then is that for the DP schemes, that actually the reversibility success didn't actually scale with the epsilon as you would expect. And I was wondering if you observed something similar, or if a lower epsilon really meant lower reversibility.
So we aren't necessarily DP experts, so well, I am not. So how we chose the parameters for all of our normalizations, which we kind of chose trade-offs which we found where we thought this seems reasonable, this is something that might actually be used, and I think the epsilon values were already kind of insane to figure out something that made sense in this sense, and I'm not sure if there was a clear trade-off where reasonable epsilons would actually mean irreversible, but at the same time you would expect some kind of trade-off. I think for all of the normalizations where you have a parameter, if you make the parameter large enough so that there's basically nothing left, then there's nothing to identify from, right?
Thank
you. Really interesting work. So I mean, you say not all the identifying information is removed. Do you have like an intuition which, like if I would prioritize what to remove, in which order would you remove stuff to get good results?
I mean, kind of the point is that as long as you leave something that's identifying left in the image, then that's something to exploit to identify people. So if you want to truly anonymize pictures where there's no chance of anonymizing, you have to remove everything, right? You might get some results that look nice if you remove the most identifying ones, but that's more an issue of, well, then your recognition method looked at specific things and wasn't prepared for the anonymization.
I have a question, which is, if you want to anonymize an image based on this, what's the recommendation? What should people be doing going forward?
Well, to some extent it depends on the use case. Best case, obviously, to just not share the image, right? So, but if you want to have some utility, if you want to maybe do machine learning on the image, but you don't care about the person, then replacing it with these kind of synthetic faces really should seem to work well. So this could be an option.
All right, let's thank our speaker again.